Hello everyone. Today we're going to talk about the spanning trees of a graph G. So assume that we have a graph with three nodes here, A, B, and C, that all of them are connected, all the nodes are connected to each other. And now we are going to draw spanning trees. So as you remember, we said that trees are a special case of graphs, but they don't have any circle, okay? So on the right side, you see a three spanning tree, 1, 2, and 3. So the spanning tree of a graph G, okay, is a subgraph of those graph, that graph G, okay. So when we are talking about subgraph, it means that so the path or the edges all come from the graph G, okay. So all nodes should be connected to each other, okay. Yeah, so we have all vertices or all nodes, and also the edges are coming from graph G, and there is no circle. So that's the spanning tree. So on the right side, again, you see three spanning trees for graph G. So there is a path from A to B and B to C. Also, as you see, there is no circle. The second one, we selected the edges from A and B, and also from A to C, and also on the last one we have the edge from A to C and from C to B or B to C, okay. So, and the question is that how we can calculate or find the minimum spanning tree, okay. So there are definitely there are many spanning trees, okay, but how we can find the minimum spanning trees. And it's obvious that what we are looking for, that if you look at like the many problems that they are making a graph, okay, like let's say that on a railroad, or I don't know, maybe a network like a computer network, okay, and you like to find the path that has the minimum cost, okay. So finding the minimum spanning tree gonna be helpful. Okay, so one way is the brute force of finding the minimum like a spanning tree. That it means that finding all the spanning trees that exist for a graph. Okay, I'm not going to go to the proof of like the number of spanning trees in a complete graph, but just for your information, the number of spanning trees for the complete graph going to be n to the power n minus 2. Okay, here in this graph you see the G, so the number of vertices, or n, is equal to 3. That means that the number of spanning tree, okay, is going to be 3 to the power 1, okay, that is going to be 3. And as you see, I draw all the spanning trees of this graph that are exactly 3. So we cannot draw any more spanning trees for the graph G, because that's all we have, okay. Now so if there, for example, there are weight associated with these things, so let's say that there's a cost of maybe 6 here, and there is 5 here, and there's another one here is 2, okay, and then you are going to like find the spanning tree that has the minimum cost. So it seems that here in this case, if we have this spanning tree of 3, it's gonna have the minimum cost, okay, because the cost from A to C is gonna be 2, okay, and from C to B or B to C is gonna be 5. So together, if we add or sum all these numbers together, it's gonna be 7, okay. But for this one, for the second one, A to B is 6 and A to B is 2, so together it's going to be 8, okay. So it's more than this 8 is more than this 7. And for the first one, A to B is 6 and from B to C is 5, okay. So between 11, 8 and 7, okay, definitely 7 is less. For finding a spanning tree for a graph G here with only 3 nodes, it's easy. You can easily just draw maybe the spanning trees and look at the numbers and some of the numbers. But when the number of nodes or vertices are high, okay, is high, so you cannot like easily do that. And as I said, there are n to the power n minus 2 spanning trees for a complete graph. Okay, so if you, for example, for a graph with n equal to 10 or 10 vertices, it's going to be 10 to the power 8. That is a very big number, and definitely you cannot easily like to find the like things. But in any case, that's going to like brute force, like finding all spanning trees, even though it's going to take n to the n minus, you will have n to the n minus 2 subgraphs or spanning trees, then maybe sorting the spanning trees by their cost and then choose the minimum value. Okay. Next, we're going to talk about like algorithms that are efficient for finding the minimum spanning tree.